In this problem, we're looking at the properties of a photon. When we talk about photon properties, there are a few things that I'm referring to. The wavelength that it has, its frequency, and its energy. It's primarily what we'll be interested about the photon and what determines how it behaves. In this case, it's a green photon, so we have a green laser pointer, so that's at 532 nanometers. And the green photon in this problem is 532 nanometers. From this information, we can get its frequency because we know that speed is wavelength times frequency. So that was true for sound waves, it's true for any waves. We can apply it here for photons as well. And that means the frequency is going to be speed of light divided by wavelength. The speed of light is a constant, 3 times 10 to the 8th. The wavelength, the only thing we need to be careful about here is that nanometers isn't meters, so we have to do the conversion. 532 times 10 to the minus 9 meters, and we get a frequency of 5.6 times 10 to the 14 hertz. It's hard to really make sense of what that number means because it's ridiculously large. 10 to the 14 hertz, that means a light wave, a visible light wave, is oscillating 10 to the 14th times per second. I don't have a good way of helping you to understand what that really means, but that's what we'll see typically for visible light waves. We get frequencies in the range 10 to the 14 hertz. Now this number is important because the energy that the photon carries is directly proportional to the frequency. So this is something new this week, that the energy of a photon is proportional to its frequency. This is what was first discovered by Max Planck, or I guess first hypothesized by Max Planck, trying to make sense out of how things are radiating light and why it doesn't agree with the classical theories of light and matter. And so we had this idea that the energy is proportional to the frequency of the light, so that not every photon or every part of the light is carrying the same amount of energy, which was what was thought beforehand. And so when you take the value of h is called Planck's constant, is 6.626 times 10 to the minus 34. This is what you're going to be measuring in this week's lab. It's a fundamental constant of nature and the most important constant when it comes to quantum physics. You take that, multiply by the frequency, and we get an energy of 3.7 times 10 to the negative 19 joules. Now, when we're talking about photons, it's fairly common to convert this energy into electron volts, which we've done a little bit of that before. All you have to do to take it from joules to electron volts is divide by the charge of divide by the elementary charge, 1.6 times 10 to the negative 19 coulombs, and you'll get 2.3 eV. Now the reason why is because the 10 to the minus 19 of something is hard to fathom, just as much as 10 to the 14th of something is hard to fathom. But when you convert the photon energies into electron volts, you get numbers that are easier to think about. And so the energy of a green photon is about 2.3 electron volts.